You've probably heard a ton about zk rollups, right? They're hailed as this key technology for scaling Ethereum, promising to make things way faster and cheaper for all of us. But here's the thing. Behind that simple promise, there's a whole world of different designs and trade-offs. It gets pretty complex. So let's dive in and sort it all out. So are they all the same? Well, the short answer is a big emphatic no. How these rollups are actually built has a massive impact on everyone, developers, users, and really the whole future of the Ethereum ecosystem. So how are we supposed to make sense of all the different flavors out there?
Okay, here's how we're going to tackle this. First, we'll cover the basics. What even is a zkEVM? Then we'll get into the great trade-off at the heart of their design. After that, we'll walk through Vitalik Buterin's amazing framework for understanding all this, check out some real-world projects to see it in action, and finally, we'll connect the dots and explain why any of this actually matters to you.
All right, first things first. Before we can get into the complicated stuff, we need to get a solid handle on the core tech that makes all of this possible. So, a zkEVM is pretty much the brain of a zk rollup. You can think of it as having two main jobs. First, it runs transactions and smart contracts just like Ethereum does. That's the EVM part. But then, and this is the magic part, it also creates this tiny cryptographic receipt, a zero-knowledge proof that proves all that work was done correctly. This saves the main Ethereum chain a ton of work. And this visual here, it just nails the key difference. A regular virtual machine, like the one on your computer, just does a task and spits out the result. Simple. A zkVM does the task, gives you the result, but it also hands over this cryptographic proof, this receipt. That little receipt is what lets the main Ethereum chain instantly verify thousands of transactions without redoing any of the work itself. It's the absolute secret sauce to scaling. But, this is where things get tricky. Building one of these zkEVMs means facing a pretty fundamental conflict, a huge design choice that every single team has to make. And it all comes down to this core trade-off. Do you want to be a perfect clone of Ethereum, or do you want to be as fast as humanly possible? On one side, you've got equivalence. That means your rollup works exactly like Ethereum, which is a dream for developers because they can just copy and paste their code. On the other side, you've got proving speed. This is all about optimizing the system to crank out those zk proofs as fast and cheap as possible, which means faster, cheaper transactions for users. And guess what? You can't have a perfect 10 out of 10 on both at the same time. So how in the world do we navigate this trade-off? Well, thankfully, Ethereum's co-founder, Vitalik Buterin, gave us a really clean framework to think about it. He basically proposed this spectrum that classifies zkEVMs based on where they decide to land between that perfect compatibility and pure performance. And this isn't just a random list. It's a super logical way to actually compare the different paths these teams are taking. And here it is. This image illustrates that spectrum perfectly. You can see it runs the full gamut, from what he calls a Type 1, which is like a perfect mirror of Ethereum, all the way over to a Type 4, which is just all in on raw speed. Let's break down what each of these types actually means. Okay, so a Type 1 zkEVM is the purest form. Its only goal is to be a perfect one-to-one carbon copy of Ethereum. No changes at all. The upside? It's huge. Every single Ethereum tool, every developer library, it all just works right out of the box. But the downside is also huge. Ethereum was never designed to be zk-friendly, so trying to prove it exactly as it is, well, it's incredibly slow and expensive. Moving down the line, we get to Type 2. Honestly, this is what most people are probably thinking of when they hear zkEVM. From a developer's point of view, it's perfect. Your smart contract code works with zero changes. But under the hood, they start to change little things like some of Ethereum's data structures, just to make generating proofs a little bit faster. It's a step toward performance, but it's still wrestling with all those zk-unfriendly quirks baked into the EVM. Now, Type 3 zkEVMs are where you see a much more explicit trade-off. They are almost EVM equivalent. What they do is they might get rid of some of the most complex, hardest-to-prove parts of Ethereum. Why? To make the system way easier to build and much, much faster. The upside is a serious performance boost. The downside is that some existing apps might need a little tweaking to work. And finally, we land on Type 4. These systems go all in on speed. I mean, they completely prioritize it. Instead of trying to prove the clunky, low-level machine code, they take the high-level code that developers actually write, like Solidity, and compile it straight into a language that's built for zk proofs. It's kind of like skipping the middleman, The result is just incredibly fast proof generation, but the trade-off is that it can break compatibility with some of the developer tools that expect that lower-level stuff. Okay, so that's all the theory, but how does this actually play out in the real world, with real projects? Let's take some of the biggest names in the ZK rollup space and see where they fit on this spectrum. This table gives us a fantastic snapshot. You've got Scroll, which is a textbook type 2, really focusing on that EVM equivalence to make life easy for developers. Then you have Polygon zkEVM, which kind of lives between a type 2 and a type 3, trying to strike a balance between the two. And then there's zkSync Era, a pure type 4, gunning for performance and low costs above everything else. And this quote right here, it just perfectly captures Scroll's whole philosophy. When they say bytecode compatibility, they're basically sending a message to developers that says, hey, don't worry about a thing. Your code will just work here. No changes needed. It's all about that smooth, seamless equivalent experience. Now, flip over to the other end of the spectrum, and you see the wild results of that Type 4 approach. Just look at these numbers from zkSync. We're talking proofs generated in under a second and transaction costs that are a tiny, tiny fraction of a cent. That's the raw power you get when you prioritize performance. So, we've covered the tech, we've walked through the types, we've seen the projects, but what does all of this really mean for the people who are actually building on and using these networks? Why should you care? At the end of the day, it's pretty simple. If you're a developer, a Type 2 system like Scroll is your path of least resistance. Your stuff just works. But if you're a user, a Type 4 system like zkSync is often going to give you the fastest speeds and the lowest fees. See, there's no single best type. It all comes down to the goals of the project and what its users and builders really need. The spectrum just gives us a clear way to understand the choices they made. Then that leaves us with one final big question to chew on. Right now, this trade-off between being exactly like Ethereum and being super fast is very, very real. But what happens as ZK tech gets better and hardware gets faster? Will that gap between the types start to shrink? Is it possible that one day we'll get a single, perfect zkEVM that's both perfectly equivalent and lightning fast? For now, only time will tell.